So I welcome you all to this first lecture of acoustics in the fourth semester. As we have planned, this lecture is a revision lecture on the topics that we have learnt in FYBSc. So to begin with, what exactly is a sound wave? So we all know that the sound waves are longitudinal waves. Typically, if you have a pipe and a piston system, and if the piston performs a forward and backward motion in the form of a simple harmonic motion, and every time when the piston moves forward, it compresses the medium, causing a compression, and when it goes back, it expands the medium, causing an expansion, which gives you the rarefaction of the medium. So you get alternate compression and rarefactions here continuously. So, and you get a formation. Now, this kind of formation where the source is performing an SHM or a simple harmonic motion is basically a sinusoidal wave. It creates a sinusoidal wave. The sinusoidal wave created over here can be written by an equation. Y, which is a function of position and time, is equal to a cos kx minus omega t. The symbols have their usual meaning over here. We are familiar with them. X is position, t is time, a is amplitude, k is wave number, omega is angular frequency, k is 2 pi by lambda, omega is 2 pi by f, t is time, x is position, x is along this axis. And the sound waves are propagated, audible sound waves are in the range of 20 hertz to 20 kilohertz. So when these fluctuations carry on, you will get these fluctuations here, and the separation between the two rarefaction or two compressions cause one wavelength or lambda, and the maximum displacement of a particle is called amplitude. So we are all familiar with these ideas. Now here are the three ways in which a longitudinal wave can be represented. So one of the most easy or most visualizing way of representing a sound wave is the middle one. You can see that this is my point where when my compression is formed, the particles which are on this side are moving towards the right. The particles which are on this side are moving towards the left. So they form a compression over here. Next compression is formed here. The particles which are on this side are moving to the right. The particles which are on this side which are moving to the left. They form another compression. So they form a compression here. They form a compression here. Since these particles are moving to the left and these particles are moving to the right, at this location you will get a rarefaction. This is one of the most visualizing way to represent it, but not the very convenient way to draw it. Remember, drawing this becomes lot of time consuming affair. So what we do, we take a simplified version or a graphical version of this. Now at compression where the pressure is maximum, we plot a pressure and position graph, and at compression where the position is maximum, the you will find I would call it as a, I can show this in this graph, I can show it as a crest. Wherever the position, or sorry, wherever the rarefaction is created in this graph, I would call it as rarefaction. Then again a compression, so a trough is a rarefaction, a crest is a compression. So when I draw this way, these are the pressure fluctuations in this one. This is a graph of displacement versus position. So displacement of any particle, this particle which is centered at the compression will not have any displacement, so it is at 0, while the particle which is here again at the center of rarefaction will not have any displacement. So displacement is variable, it goes on increasing at the middle, then goes on decreasing towards this side. So this is the maximum displacement in one direction. This crest represents the maximum displacement in the other direction. Now you can notice from these two phenomena that your pressure fluctuation and your displacement fluctuations, they are phase delayed. So when this reaches at peak, this is at 0. When this becomes 0, this reaches at peak. When this reaches at its minimum or the negative peak, this reaches at 0. So you can see that there is a phase difference of pi by 2 or 90 degree. Okay, so this phase difference is important. Do remember that this point is called displacement antinode. Listen to me very carefully, because this I am going to use for many times in practicals and lectures. This point is called displacement antinode. Okay, while this point is called node, displacement node. This point is again displacement antinode, and this is displacement node. So a node is point, an antinode is a point where the value of the displacement is maximum, and the node is a point where the value of displacement is minimum. If you come to the pressure graph, then you will find that the pressure fluctuation is minimum here. So this point is pressure node. Node means the fluctuation is minimum. Pressure fluctuation is minimum. So this is pressure node. While this is pressure antinode, because the pressure fluctuations are maximum. So you can see, so on and so forth, node, antinode. So you will see that whichever is your displacement antinode is your pressure node. Whichever is your displacement node is your pressure antinode. Means wherever the pressure fluctuation is maximum, wherever the pressure fluctuations is maximum, the displacement is minimum. I leave this for you people to explore. Read the reference and explore. Why does it happen? Why wherever the displacements are minimum, the pressure fluctuations are maximum? Do explore this. This is very important for the course. So important points. Normally most visualizing form of sound wave is this. But in practice, we always plot a graph of either displacement versus time or pressure versus time. That is one thing we have to remember. The other thing we have to remember is the pressure versus position, pressure versus displacement versus position. The other thing we have to remember is they are phase delayed. There is a phase difference of pi by 2. Thirdly, whichever is the displacement antinode is your pressure node. Whichever is our or rather node and antinode, we can strictly talk when we study stationary waves. Here we can simply say the pressure is whenever the displacement is maximum, the pressure fluctuations are minimum. Whenever displacement is minimum, pressure fluctuations are maximum, so on and so forth. Before we end, we will do a very quick observation. I have a small cylinder over here of which a small sized sample I have taken. It has a cross-sectional area S and the distance delta x. If the sound wave is passing through it, then the ends of the cylinder will be displaced and they need not be, and remember in quotations, need not be. They may be, they may not be. I'm saying they need not be of the same amount. So if this edge of the cylinder displaces, say by y1, this may displace by y2. Okay, so the displacement y in this direction is function of the position x and time t. This displacement of this end is a function of position x plus delta x and time t. So the change in the volume, like final volume minus initial volume, this black and white cylinder minus dark blue, light blue cylinder, the difference in the volume would be given by this equation. So S of y2 minus y1, and which is nothing but positions of y x plus delta x comma t minus y of x comma t. If you divide it by the original volume, which is S delta x, and take a limit delta x tending to 0, then you will get the first principle of derivative. S cancels off y of x plus delta x minus y of x upon delta x, which give you the derivative of y with respect to x. So change in volume per unit volume as the wave progresses is dy by dx. Now we know that the bulk modulus of the medium is given by minus P dash dV by V. So dV by V is nothing but dy by dx, and therefore the pressure in the medium can be given as minus B dy by dx. But remember, this is not a constant quantity. This keeps changing. As this changes, the pressure fluctuates. So the pressure fluctuations are going to happen. Now, as we have seen that if you have a sinusoidal source here which performs SHM in the previous drawing, then the y displacement will happen sinusoidally, and therefore I can introduce y as cos kx minus omega t, and its derivative will become sin kx minus omega t. So this gives me the pressure as a function of position and time. In other words, it gives me the equation for the pressure wave through the medium. This is the equation for the pressure wave. Remember that this is the maximum amplitude. BKA is the maximum amplitude of the pressure because sine function has a maximum value plus minus 1. So P max is BKA. This is my maximum pressure for the sinusoidal sound wave. where B is the bulk modulus, K is the wave number, and A is the amplitude of the displacement amplitude. So the pressure at any moment is maximum pressure at any moment is proportional to the amplitude. Please note that point. P max is proportional to A. Now, how do we get velocity of sound wave? So let me do this discussion and maybe we can stop. Typically, the wave of velocity of any wave in a given medium is given by this equation. Square root of restoring force returning the system to equilibrium divided by inertia resisting the return to equilibrium. In fact, it's a square root of elastic properties upon inertial properties. Elastic property ensure that the elastic properties ensure that the medium will come back to the equilibrium when it is disturbed. Inertial properties tries to resist that equilibrium. So for example, if the elastic forces are strong, the velocity will be more. If the inertial forces, now inertial forces means mass. If the mass is very high, heavy, medium, then in that case, the velocity will be less. So you will observe this if you have a very take two kind of strings, a thin string and a little thicker rope. Stretch them, pluck it at the center and try to observe their motion. So you will find that the thin strings, they vibrate very fast. In fact, they vibrate so fast that you can't even observe their vibrations clearly. They are not visible clearly. But if you have thick ropes, then those vibrations happen and they are fairly visible. So therefore, these two things determine the velocity of a wave. Think about what will decide the velocity of light wave in a medium in space. Next year you are going to do relativity and you will encounter this problem and you will encounter this equation again, that how is the velocity of light wave defined or decided. But remember, these remain the central ideas in the velocity of a wave. Now, in case of transverse wave, it is tension in the string divided by mass per unit length. So if the string is more taut, sonometer, guitar, etc., the velocity is high. Tension is less, velocity is less. Mass per unit length, again inertia. Tension is elastic property. Mass per unit length is inertial property. Heavier the mass, lesser will be the speed. Now, how do this formula transform in case of sound waves? Very straightforward. The inertial properties are given by bulk modulus. I'm sorry. The elastic properties given by the modulus of elasticity, which is bulk modulus in case of fluids, and in case of fluids the inertia is given by density. Higher the mass, higher the density, less will be the velocity. Higher the bulk modulus, more will be the velocity. Now bulk modulus of a gas is gamma p, you all know that, and this formula takes the famous shape of famous Newton's formula, gamma p by rho, of course with Laplace's correction. And if it's a solid medium, Then the bulk modulus is replaced by Young's modulus. So say it's a linear medium, linear rod, railway track, etc., etc. Then V is equal to root of Y by rho. So this becomes the velocity of sound. We can stop here today in this class.